Hello, this is Electrical Circuits tutorial series, part number 8, and we'll be doing a combination circuit analysis. So we're going to use a simple combination circuit. And the first thing that we have to do is we have to find out which is the parallel portion, which is the series portion of this circuit. And so we'll trace it like we have before, and here we have one path up to this point where we have a node, and we go this path or this path. So R sub 2 and R sub 3 are in parallel. So we come out here and back connecting to our node. So this is our entering node and our exiting node, and then we come through one path through R sub 1, and there's only one path there, full circle to the power source. So R sub 1 would be the series portion of this circuit. R sub 2 and R sub 3 would be the parallel branches in the parallel portion of the circuit. So we're given us a total voltage of 120 volts. Resistances of R sub 1 is 14 ohms, R sub 2 of 10 ohms, and R sub 3 is 15 ohms. We do need to find the total resistance, and but before we can do that, we need to find out what our parallel resistance is. We need to reduce it to the equivalent of a series circuit and then redraw the circuit. We could use this, since there's only two branches, we could use the product over sum, where it'd be R sub 2 times R sub 3 divided by, open our parentheses, R sub 2 plus R sub 3, close our parentheses. We'll get the same answer, but we're going to go ahead and use the reciprocal formula like we have been using. So that's R sub 23 is equal to 1 divided by, open our parentheses, 1 over R sub 2 plus 1 over R sub 3, close our parentheses. R sub 2 will be 10 ohms and R sub 3 will be 15 ohms. And when we plug that in, that gives us a 6 ohm total for the parallel portion of the circuit. Now the smallest branch resistance of the parallel portion of the circuit is 10 ohms, and that 6 ohms does fall underneath it, so it meets the criteria, the rules we have for parallel circuits. Now we're going to redraw the circuit. The reason we redraw the circuit is so it's not so confusing, especially when you get into more complex circuits. But by redrawing it, we know what kind of a circuit we have and are working on, so we also know what circuit rules to use. So we've redrawn this circuit as a series circuit now. We come from the power source, we come through here through the R sub 23. This resistor is symbolizing our parallel portion, and with still one path all the way back up to R1 back to the power source. So we do have a series circuit at this point. So we need to find the total resistance, and that's going to be equal to R sub 1 plus R sub 23, since in a series circuit the sum of the individual resistances equals the total resistance. So 14 plus 6 will give us 20 ohms for the circuit. Now we can find our current total, and our current total will be the voltage total divided by the resistance total. So 120 volts divided by 20 ohms will give us 6 amps. Now because we are working with a series circuit, and the current remains constant, I sub t is equal to I sub 1 is equal to I sub 23, so we can populate both of those with that 6 amps also. Now, going on here now, we need to find our voltage drops. So V sub 1 is going to be equal to I sub 1 times R sub 1. I sub 1 is 6 amps, R sub 1 is 14 ohms, and that'll give us 84 volt total drop for V sub 1. V sub 23 is equal to I sub 23 times R sub 23, and so I sub 23 is 6 amps, and R sub 23 is 6 ohms that we calculated earlier using reciprocal formula, and that'll give us 36 volt drop there. Now as you notice, because of our series circuit rules, the sum of the individual voltage drops must equal the total voltage, and so that means V sub t is equal to V sub 1 plus V sub 23. So 84 plus 36 is 120 volts, so we do meet that criteria. Now we're going to redraw the circuit again, and we've redrawn it to the original circuit, and we're needing V sub 2, V sub 3, I sub 2, and I sub 3. Now, in a parallel circuit, voltage remains constant, so V sub 2, 3 is equal to V sub 2 is equal to V sub 3. So we can populate both of those with the 36. Now, this being said, we need to make note and keep in your memory that if either one of those parallel branches has a series string in it, we have to redraw our circuit a couple more times. We would have to combine those two into one load before we could do the reciprocal formula of it. So keep that in mind if you get one like that. Now I sub 2 is going to be equal to V sub 2 divided by R sub 2. So we have 36 volts for V sub 2, and R sub 2 is 10 ohms, and that's going to give us 3.6 amps. I sub 3 is equal to V sub 3 divided by R sub 3. We have 36 volts for R sub 3, or V sub 3, excuse me, and 15 ohms for R sub 3, giving us 2.4 amps for I sub 3. Now, to make sure that we did the parallel circuit currents properly, remember I sub t is equal to I sub 2 plus I sub 3, giving us that 6 amps. So our current in equals our current out, and so we did our math right. Now all we need left to do is find our power that we dissipated, the total power and the power dissipated by each individual component. So P sub t is equal to I sub t times V sub t. So P sub t would be 6 amps times 120 volts, giving us 720 watts total. Our P sub 1, power dissipated by the first load, would be I sub 1 times V sub 1. I sub 1 of 6 amps, V sub 1 of 84 volts will give us 504 watts total. P sub 2 is equal to I sub 2 times V sub 2. I sub 2 is 3.6 amps times 36 volts, leaving us with 129.6 watts. P sub 3 is equal to I sub 3 times V sub 3. I sub 3 is the 2.4 amps times the 36 volts of V sub 3, giving us 86.4 watts dissipated at the third load. Now we can do our quick check. The sum of the power dissipated by the individual components will equal the total power. And so P sub t is equal to P sub 1 plus P sub 2 plus P sub 3, giving us 504 plus 129.6 plus 86.4. And that does return the same total power of 720 watts. This concludes part 8 of our electrical circuits tutorial series. Thank you.